Hello and welcome to another day of Advent of Code. Today's solutions and techniques will be day 7. I feel like day 7 is the first day that's actually kind of tricky, so hopefully after my explanation it'll make a little bit more sense. I'm going to show you 2 different ways to solve it, and let's jump into it. Okay, so the problem today is we are tasked with a description of a bunch of bags. And those bags contain bags, and the bags contain bags, and the bags contain bags, and it's bags all the way down. And we're tasked with answering 2 questions here. The first question is, how many types can contain a shiny gold bag? So when I heard this, I was thinking, okay, well, what are all of the outer things that could be above a shiny gold bag? And part 2 is how many things are contained within a shiny gold bag. But funny thing, when I went to solve this for Advent of Code, I actually accidentally solved the second problem first and then had to go back and resolve the first problem. But anyway, so given this input here, my immediate thought was jumping to graphs. And I don't know about you, but I don't like dealing with graphs, and honestly, you know, in actual practical programming, I don't spend much time working with graphs. That said, I know how to work with them, and so hopefully I'll show you how I worked with them. But if you need to visualize this, because, you know, some people are a lot more visual, I made a little diagram of just this first line. You can imagine the same thing being expanded out for all of the different lines. So this is light red bags contain 1 bright white bag and 2 muted yellow bags. And so, you know, this light red bag contains these other 2, so you can think of it as a directed graph with weights on the edges. The weights being like, you know, how many are in that particular place. So if you traverse from light red to bright white, you add a bag. If you traverse from light red to muted yellow, you add 2 bags. And you can imagine all of the bags kind of fitting into this as like a big graph. I only drew these 3 nodes from that one line, but you can imagine there being a lot more. Now, when I like to represent graphs, I usually reach for a couple different strategies. One is if like the points on the graph are in a coordinate plane, I might plot them using a coordinate plane. But in this case, I mostly plotted this by using a mapping from the parents to the children, or the reverse mapping, because we actually need the reverse mapping for part 1, where we map from the children to the parents. And so that helped me kind of have a concrete data structure for dealing with these graphs here. And then I can deal with the edges by just looking up the parent or looking up the child in that mapping. But as such, because we have 2 different representations based on the problem, we're actually going to do 2 different parsing approaches here. So this is the mapping that I'm looking for the first part. The first part, we're trying to find the parents, so the ones that contain this. And so if we look at a light red bag, if we look at a bright white bag, we know that one of its parents is a light red bag, and so that's what the first part is here. You'll also note that dark orange bags can also contain bright white bags, and so dark orange ends up in here. And we're going to build up this entire mapping as part of implementing this parsing here. Now note for part 2, we're actually going the opposite direction. So we start with a shiny gold bag, and we're trying to figure out how many things that contains. And so we need to go from the parent to all of its children. So we're mapping here, you know, from shiny gold to, I should actually probably copy this down below again so you can see it when we're working on it, because there's a lot of output here. But you can see, like, you know, bright white is right here, and it contains 1 shiny gold. These are sorted alphabetically, so it doesn't necessarily match up with these. So I probably should have sorted these a little bit better, but I just printed this from my actual execution of the program. But yeah, these are the 2 parses that we're going to implement. I'm actually going to show you how to do this with regular expressions, but you can parse this in a bunch of different ways with split or whatever. I just found this a lot easier to implement with regular expressions. So we are going to import, oops, oh, that would have thrown this off. Import RE, and I'm going to make 2 regular expressions, one to grab this part of the string and leave this rest part of the string in there, and then another part to try and parse each of these things on their own. So the first regex is going to be our line RE, and we're going to do re.compile. I did a video on regular expressions that will be in the description, so check that out as well if you need a crash course on starting regular expressions. And I showed this to a non-technical person, and they were able to write regular expressions in about 30 minutes, so hopefully it can help you as well. But anyway, we need to capture this part here. So we're going to make a capturing group, and we need to capture a white space, a non-white space string, then a white space, then a non-white space string. When I did this problem, I actually just did a non-white space character plus, and then a non-white space character plus. But you can actually just use word character here, \w. So that makes this a little bit easier. And then bags contain, and then dot star or dot plus for the rest of the string here. So we'll get two groups out of this. We'll get the parent group name, and then we'll get the rest of the string. The reason that we have to do the rest of the string in kind of like a two-phase parsing is because there could be 0, there could be 1, or there can be many bags inside of a single bag. And so we have to, potentially loop over multiple bags there. And so let's do the child re.compile, and in this case we're going to be matching a number and then a double white space character thing again, and we need to capture both of those. So we're going to do \d plus, although looking at the input, all the inputs actually use only a single digit number, so you could cheat here and just use \d, but I think it's better to generalize this. I actually abused this fact in my SQLite solution because I was not interested in doing the more complicated parsing there. But we'll do the same, \w plus, \w plus here, and we'll capture that as well. Note for this regular expression here, I used anchors here to make sure that we're matching the entire string. But for this one, we're going to be using search instead of match. So we actually don't care about the boundaries, and it'll kind of be a sliding attempt of matching inside of here. And so we'll actually match both of those there. But those are the two regular expressions we're going to use. For part one, we're trying to map from a key to a list of things, and we actually don't know what things will exist or not, so we actually have a tricky problem with our dictionary here. I'm actually going to use a different type than dict here, so from typing import default dict, and I did a video on this as well. Default dict is really great for interview questions. I also forgot to import the other types from typing import dict, and we probably also need list as well. But I use default dict to solve this, and the nice thing about default dict is you can insert stuff into it, and you don't really have to do checking as to whether the key already exists. It can just simplify a bunch of your code here. And we'll actually use the fact that it's a default dict later to ignore some things that don't have any parents. Excuse me. So I made this thing called parents, and I assigned that to a collections. Oh, right. Oh, what happened there? I must have hit page up. Default dict. I assigned this to a collections.default dict, and default dict takes the type of the value that it's going to construct. So the way it works is when you access a key that doesn't exist, it will build this for you. So we will always have a list if we look in there. And we need to loop over our input lines. And again, for line in input s.splitlines, this will look familiar if you've done some of the other puzzles. And we need to actually do our parsing here. So line match equals line re.match line. If you're working with MyPy and doing type checking on yours, you'll want to do assert line match. This is also just a good idea to make sure that you're matching things properly. I also put line here just so the error message is helpful for debugging that. I hope we don't have a bug, but we'll find out in a bit. And so from line match, we have, if we look at group 1, we will get the key for the parent part. And we need to loop over everything in this part to get the children. And so we're going to use find all. And and we actually don't care about the number here, so we're going to ignore the number and only look at the color. For number child in child re.findAll line match 1. So this is going to refer to this second group here, the part that we just kind of discarded. And we need to update this parents mapping based on this relationship. So what we're going to do here is the child is actually going to map to the parent instead of the other way around. So we're going to do parents child dot append line match 0. So line match 0 here is the parent. And now, of course, we used a better set of variable names here. We might say parent parent equals line match 1. Oh, I was off by 1. Sorry. Groups are 1 based because the 0th group is the entire match. It's actually a good thing that I did this. And rest equals line match 2. So we should put rest in here, and we should put parent in here. And then given all of that, we can return parents, and that'll give us this entire parsing for part 1. Let's actually run that. Parsing.py. Typing import tuple. That's actually good that it errored because the second part we haven't implemented yet. And let's see. I mean, the printout is a little bit difficult to read, but we did get the same output that we got on the left-hand side. So it's a default dict, so it's not exactly a dictionary here, but it acts like a dictionary, so we can continue to use it that way. So you can see that's how I did the parsing for the parents. And now we're going to do the parsing for the children. And it's actually going to look a lot the same as before. I'm actually going to copy and paste this bit of code here, because this parsing part, actually we can do this part. This parsing part is going to be about the same. So we'll come down here. The thing that we're going to change here is we're going to have a mapping from the parents to their children now. So we're going to have a dictionary mapping to a list of strings. I actually didn't need default dict here, so I can just use a normal dictionary because we're not modifying the dictionary after creation. We're just putting things into it. So we have n and child here, and I'm actually going to build a list, children equals, and we're going to turn this into a comprehension. I did a video on comprehension, so I'll link that as well. And the reason we're going to turn it into a comprehension is we need to intify this string here. And so once we have children, we can do colors parent equals children. Children. And then return colors. So that should get us our parsing for part 2. We can see bright white, dark olive, dark orange, dotted black. So these are the ones that contain no bags. Dark red, muted yellow, shiny gold, and vibrant plum. Cool, so that's the parsing. That gets most of that out of the way. And we're going to be using these 2 mappings to solve the rest of the problem. But anyway, there's parsing for part 1. And here's parsing for part 2. They're very, very similar in structure. Okay, let's jump into part 2 now. Sorry, the part 1 now. I'm going to keep the parsing open just so we can see this input while we're working on it. And the way I solved this was actually not with recursion, but this problem and a lot of graph problems solve extremely easily with recursion. So I'm going to show you a recursive solution first, and then I'm going to show you an iterative solution next. I prefer the iterative solution because it runs a little bit faster, especially in languages that have, dynamic interpreted stacks that are expensive to do function calls, like Python. But in other languages, the recursive version will actually compile to an iterative version, so it doesn't actually matter. But anyway, what we want to do is compute the number of bags that can be parents. So if we start at shiny gold, this is pretty easy to figure out by hand. So shiny gold has the parents bright white and muted yellow, so those are 2 possibles already. Bright white has the parents light red and dark orange, so that's 2 more parent possibles. And you'll notice light red doesn't actually have any parents, and neither does dark orange. So those are the 4 possible. But we're going to try and represent this in code as work to do. So I'm going to make a compute helper. Compute helper, and this is going to take a color as a string, and it's going to return the number of, it's going to return, a set of strings, which is all of its parents, including itself. And so we need from typing import set. And the nice thing about set here is it'll eliminate any duplicates. So if, for instance, bright white could also contain muted yellow, we don't double count muted yellow. And we're going to do return compute helper. I'll actually show you in a minute this is going to be off by 1, and why it's going to be off by 1, but we'll get to that in a second. So our compute helper here, we need to return the length of it. That'll tell us the number. And so our compute helper is going to include itself and then say how many of its parents are also included. Actually, we could avoid including. Can we avoid including ourselves? Maybe. Yeah, I think we can avoid including ourselves. So we can just do, oh no. Yeah, no, we have to include ourselves. Okay. Ret equals color. So this is a set just containing the color that we had. And then we need to add all of its parents. So for parent in input color, ret union equals compute helper color. And I should, give a docstring so this is easier to understand. This is self and parents containing color. That's kind of our helper here. So you can see that we are, self and then all of the parents, and we're recursing here. So we're calling the same function that is our self. And if we return ret here, and when we run this, you'll note that shiny gold gets passed in here, so it's actually going to be part of this set, and we don't want shiny gold to count, so we're actually going to subtract out shiny gold here, because shiny gold is not included in itself. Otherwise, you would have infinite bagception. And if we run this, recursion error. Oh, I made a typo here. This is supposed to be parent. Whoops. And that's, again, like one of the reasons why recursion is kind of tricky. Like often you'll end up in these kind of difficult to debug scenarios. Key error light red. Oh, right. So we actually cheated a little bit on the first problem. And we had a collections.default dict here instead of a normal dict. So I'm just going to put that back in here. That is going to make it slightly easier for us to ignore keys that have no parents, such as light red here. And so this is how you initialize a default dict with a default value. And you'll see if we run this, we get 4. And if we actually print out the compute helper here, shiny gold, you'll see that it contains, shiny gold, dark orange, light red, muted yellow, and bright white. So those are the things that we expected here. But that's the solution. That's the solution to part 1 using recursion. So recursion. But I preferred to solve this without recursion. Compute iterable. Also, if you've worked with graphs before, this is a depth first search. So we are using a stack, and in this case, the stack is the recursion stack to go to each of the leaf nodes and count them all there. But I preferred to do this iteratively, and the way I did this was a scene colors as a set, and to do as a list. This is actually our stack, but we're using a data structure instead of a function called stack. And this is shiny gold. And we know that we have more work to do if to do still has something in it. So I'm going to do a while loop, so while to do. And then color equals to do dot pop. So we're going to take the last one off and then try and process its parents. And so we can do scene colors dot add color. And then we can do for parent in, actually we can just do to do dot extend input color. So this puts all of its parents into this to do stack. And so this will run until we exhaust everything. And this code is actually exactly equivalent to this here. And if we, print scene colors here, and then return len scene colors minus shiny gold, you'll see that, oh, we didn't actually do this one. Iterable, should have been iterative. You should see that we also get 4 here for this one, and we get the same set here. But anyway, that's kind of 2 ways to approach part 1, the recursive way and the iterative way. And I guess we can jump onto part 2 now. Part 2 is actually going to look a lot similar to this, but instead of iterating in this way, we're going to iterate downwards. So let's start with part 2 now. Part 2.py. Now, part 2 actually has a little bit more tricky bits in that we have to keep track of the numbers here. And one thing that tripped me up a little bit when I was thinking about this problem is if one bag contains 2, let's say white contains 2 red and red contains 2 blue. So the one white contains 2 reds, and so we have 2 red bags, and each of those 2 red bags contain 2 blue bags. So that's 4 blue bags. So we actually have to multiply as we go downwards. And again, I'm going to implement this both recursive and iterative. So we're going to make another compute helper here. And this is going to take n as the number of bags and the color, and then return the integer for everything that's summed below it. So n is an integer and color as a string, and we're going to return an integer here. And so what we're going to do is we are going to say, ooh, do we want to, yeah, we're going to say the return value is equal to n, so that'll count ourselves, and then we need to count all of our children. And so for child and child in input color, ret plus equals n times, or I guess we can just do, yeah, compute helper of n times child n. So this is kind of that multiplication that we need to do here, and then child. So this is going to do our recursion here. So we would check like, so if we do return compute helper 1 shiny gold, and of course we need to also subtract 1 here because we are counting the shiny gold and we don't actually want to count the shiny gold here. So we'll call this compute recursive, and if we run this, oh, that's part 1. You'll see we get 32. So the way this works, we call this function, we jump in here, say this is the first iteration where n is 1, and we ask for shiny gold bags. So then shiny gold has 1 dark olive and 2 vibrant plums. So we're going to go through this loop, and we're going to call 1 times 1 dark olive. So that'll call compute helper with 1 and dark olive. That one's not super interesting. Let's do the one where it calls 2 with vibrant plum. So 1 times 2 with vibrant plum. So we re-enter this function again, and now ret is 2, and the color is vibrant plum, and vibrant plum has 5 faded blue and 6 dotted black. So we have 2 times 5 of faded blue, so 10 faded blue and 12 dotted blacks. And so then we, jump into that and recurse downwards until you've handled the entire graph. And again, this is also a depth first search. Now I didn't like doing this one recursive as well, so I did this one iteratively. And we're actually going to use the same sort of approach that we did before. We have a total and we have to do with a number 1 shiny gold, and in a way this data here, you can kind of think of it as the parameters to this function, and that's how we're accumulating this data as we go. And so again, while to do n comma color equals to do dot pop, that will get us the last value from the to do. And then for child and child in input color, we want to do dot append n times child n, and then child. And we also need to sum all the values as we do this. So we need to add the value as we pop it. So total plus equals n, and of course at the end we need to subtract 1 because we counted shiny gold already, and then return total. And this will loop very similar to how this one looped up here. And in fact, I could do this as a list comprehension as well. I could do to do dot extend n times child n for child n comma child in input color, and that this line is the same as this for loop here. But maybe a little bit more compact. I'm gonna leave it as the for loop because I think it's a little bit easier to read on the video. And we have to call this down here, compute iterative. So that should give us 32 twice. But anyway, that is how I did these 2 problems. Open back up part 1 so we can see those 2 solutions again. And that's how I solved this problem. And they are both depth first searches, and they use slightly different graphs for both of them. Or slightly different inputs for both of them, but they're both graph traversal problems. Anyway, hopefully this was helpful. Hopefully you learned something, and I'll see you for the next day. Bye.